These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. Okay, so to start with, I'd like you to try to figure out the torque from force 1. How would you go about figuring out the torque from force 1?
Okay, draw it here. Okay, so then I know, okay, so first I know it's going to be a clockwise torque, so it's going to be negative, and so it's in equilibrium.
Let's see. Actually, no, we're not given that information that it's in equilibrium. We just want to figure out the torque from force 1.
Okay, so we know, so the formula for the torque is the force times the moment arm. So we know that the moment arm is 3 meters and the torque is 10 newtons. But I need the distance from the application of the force to the pivot.
Okay.
So then it's going to be 10 cosine 20. Is that right?
Okay. So yeah, go ahead and finish the problem, and then I can give you some help if you got stuck. So what would be the calculation you would do?
So I would say 10. I'm actually not sure. I know. Okay, so I don't know.
Okay, that's fine. I just wanted to see where we're at. So why don't we talk about this together?
Yeah.
It turns out that the most important skill for statics is finding the torques. A lot of people that have trouble with statics, it's not the statics itself, but oftentimes just finding the torques. So let's make sure we know how to do that. Torque is actually a kind of a, it's not that easy to calculate it, so we should go through that. Now, do you remember what's the symbol for torque?
Tau.
That's right, Greek letter tau. Did you get the email I sent you? I just sent you an email a few minutes ago.
No.
Why don't you check for that? I sent you a couple of handouts that might be useful today. See if you got that.
Okay, I have it. Let's see. Let's download them.
And if you can print those out, and have those in front of you while we're going through this, that might be helpful.
So I've printed the one on rotation
Great.
already.
Okay, good. And when you have that printed out,
okay.
I guess we're looking at, page 4 of that handout, which is the one on how to find torque. Page 4.
Okay.
Okay. So like I said, this is a little bit confusing, so it's good to have a systematic method for that. All right. Do you have that, or are you still printing that?
Yeah,
okay.
It's here.
So now, one thing that's confusing is that there's 2 different methods for finding torque. There's the R method and the R perpendicular method. Most of the time, usually, you can use the R method. So let's start with that. So that's to be the left-hand column here. So step 1 is to draw the axis of rotation, or the pivot point. Now, in this problem, you were just taking it for granted that this fulcrum here would be the pivot point, and I think that was a good assumption. So it would make sense that if we're going to rotate around this point. So that's a good thing to choose as the pivot point. Step 2, you draw the force at its point of application. I already did that for you. Where is the point of application of the force, then? What I mean by that is this point here. This would be the point of application of the force, and we already know that. Now, step 3 is the key. We have to draw R. And R is a vector that goes from the axis of rotation to the point of application of the force. So that's really the key. The reason that people have trouble with torque is because they get lazy and they don't draw R. So we need to draw the R vector here. So where would R start in this case? It would start at the pivot. And where does it go? It goes to the point of application of the force. So we would draw R like this. I'll call that R1 because it's the R for this force. So that's our R vector. our R1 vector. Next step is to determine theta. Theta is the angle between F and R. So what would theta be in this problem?
20 degrees.
That's right. Now the key thing is theta is not any old angle. It's got to be the angle between F and R. So very often people are given an angle that's not theta and they just assume it's theta. But in this case, 20 really was theta. Step 5, now we're ready to plug into our equation. So we've got here torque is plus or minus R F sine theta. The first thing we have to do is figure out the sign of the torque. That's something you'd already figured out on your own. You had seen that if this was the only force, it would cause a clockwise torque. But you were choosing counterclockwise as your positive direction, so you said the torque was negative. So it's good that you did that. Now, I don't know if you've watched my other videos. I like to use a dot to indicate when a symbol stands for a magnitude. So this just means the magnitude of R and the magnitude of F. So what should we plug in here for the magnitude of R?
So R is 3 meters. It's positive.
That's right. We just plug it in without a sign because all we want is the magnitude. And then what should we plug in for the magnitude of F?
10 newtons.
10. Good. And what do we plug in for theta?
20 degrees.
You have your calculator with you? Go ahead and do this calculation.
Okay, so that is 10.3.
So what was the torque?
The torque is 10.3 newton meters.
There was actually a mistake there. It's negative 10.3.
Oh, negative, right.
All right.
Okay.
And that's a big deal. When we get to the statics problems, we'll see one of the biggest sources of mistakes in statics problems is forgetting the negative signs. So we have to work really hard at this point to remember to always put in the sign. Okay, and what did you say the units were?
Newton meters.
Good. How did you know the units are Newton meters? Well, you could figure that out from the formula. Force is in newtons, R is in meters, and trig functions have no units. Okay, so this is the first really crucial skill to get down. If we can get down the skill of finding torques, that'll really help us with the statics problems, because this is the most important part of a statics problem. So I think you had some of the right ideas on this problem, but it didn't sound like your confidence was very high. So these are the 3 parts that we have to put together here, R, F, and theta. And the real key here is to not be lazy, but to always be willing to actually draw the R vector. Just drawing the R vector can make things a lot clearer. Usually instructors don't draw the R vector, but they're kind of doing that in their head. But a beginner, it's important to actually write that down. Okay, so what are the, and we just went through the step-by-step method here. At the beginning, it's good just to keep looking at the handout and making sure you're doing all 5 steps in the left-hand column over and over until it becomes second nature. So where do people go wrong here? Let's see. So one mistake that people make is not drawing the R vector. Another mistake is using the wrong angle as theta. So remind me, what was our definition of theta? Theta is the angle between who and who?
Between F and R.
That's right. So you got to make sure you're using the right angle. And then a third mistake that people tend to make is they forget to determine the correct sign. So maybe it's good to start the formula with the plus or minus to remind yourself that it's your job to figure out the right sign. Okay, so let's do work on that and make sure that we have those skills down. So for example, let's say we've got this. So I'd like you to go through that step-by-step process again now and figure out torque 2.
Okay. So in this one, I would say the R vector is 4 meters, and the force that's being applied is 20 newtons, and the angle is 30 degrees. So then I would say it's 4 newtons times 20 times sine of theta, which is 30. And I know that it's counterclockwise torque, so it's positive.
Okay, so go ahead and finish the problem.
So then I know that torque is 40 Newton meters.
Oh, that's right. What would be the sign on that?
Positive.
Let's get in the habit of always putting a sign. Usually people don't write a positive sign in front of positive numbers, but that would be a good habit for us, because if we always write the positive sign in front of positive numbers, that will remind us when we need to put the negative sign in front of negative numbers. Now, did you draw R2?
So R2 is from where the force is being applied back to the pivot point.
That's right. Technically, it's from the pivot to where the force is being applied. Okay. That doesn't really matter very much. So that would be a good thing to actually write. That's how we know that this 30-degree angle is the actual angle that we need in this case. Okay, so that one went more smoothly, so that was correct. So now let me give you this example. Let's say we've got this. And let's figure out torque 3.
Okay. So torque 3 is also going to be counterclockwise, and it's going to be 5 newtons times, would that be sine of 90 degrees since it's perpendicular to R?
Okay.
And then times 8 meters. So that would be positive 40 Newton meters.
Okay, it's always good to start with the general formula. So
okay.
Here's the general formula that we were using. Okay, great. So did you draw R3?
So R3 would be from the pivot to the point of application of the third force.
Good. So let's see here. We can see that the magnitude of that is going to be 8. Now, what did you plug in for F?
5 newtons.
Good. Now, this is in what usually is considered the negative direction, right? So why didn't you plug in -5? That was actually a good decision, but that's a common mistake people make. Remember, that's what this dot is supposed to remind us of. We're not plugging in the sign for the force, just the magnitude. So it's good that you didn't plug in -5. We're just plugging in the magnitude because you'd already figured out the sign on your own. Notice that even though this force is in the negative direction, the torque is actually positive. So that shows us that it's not the direction of the force that tells us directly the sign, but you have to figure that out on your own. Okay, right. And then you took the sine of 90, which was 1. I didn't draw the angle.
Yeah, I usually find that it's easier to figure out if it's a positive or negative torque first.
Yeah.
And just conceptually think about it, and then
that's great.
Find what the torque actually equals.
That's right. I think that's good. That way you don't forget to do the sign. So once you've done that, there would be no point plugging in signs for the variables because you've already figured out the sign. Okay, and you saw that the angle here was 90, and the sine of 90 was 1. That's a common situation. The whole point of this is only the component of the force that is perpendicular to R causes rotation. Well, in this case, the entire force is perpendicular, so the whole thing is causing the rotation. So the sine of 90 was 1. That was good. Let's also consider let's figure out torque 4. All right, so I'd asked you what was the torque from this F4 force, and I think you figured that out. Whoops, put that back. So here you can't draw R, because R would start at the pivot and would also end at the pivot, because that's where the force is being applied. So R is 0, and therefore the torque is 0.
Right.
So it's good that you were aware of that. That's something that can be useful to us when we're doing statics problems. This should just be common sense. Your common sense should tell you that if you pushed right on the pivot, you could not cause any rotation. All right, good. So that was correct. Now let's figure out the torque from force 5.
So that would also be 0.
Excellent, great. And how did you know that?
Because you'd be pushing parallel to the beam or whatever that is, so that when it causes it to rotate.
Okay, good. That's a good answer. Now, that was an answer that relied on your intuition. Your intuition tells you that if you push in this direction, you can't cause rotations. That's a good answer. Let's also confirm that mathematically. Did you draw R5?
So R5 would be from the force to the pivot, which would be 11 meters.
Good.
But then there's no perpendicular distance.
So there's no component of the force that's perpendicular to R5. That's right. And to continue thinking about that mathematically, so what would be the angle, theta? What would theta 5 be?
0.
Right. Or actually, the way I've drawn them, I've drawn R to be anti-parallel to the force. So in my picture, theta would be 180.
180.
But it doesn't make any difference, because what's the sine of 180?
0.
That's right. So either way, you would end up with a 0. Okay, very good. All right, so that's a good review of those basic ideas for calculating torque. The most important thing there is to remember, what's the definition of theta?
So the angle between R and the force, and R and F, the point of application of F.
So theta is the angle between R and F. So we want to make sure that we're using the right angle for that. Good. Now, in this picture, I'm not going to tell you how big F is. So what could you say now about the torque from force 1? How could we write down an expression for the torque from force 1?
So then it would be F1 sine of 90, which is just 1, times 3 meters.
Okay, so what would you get as your expression for the torque?
So you would have like 3 meters times F1, or times F1. And it would be positive.
Okay. So again, we'd want to draw the R vector. Whoops. So the magnitude of R would be 3. Now in this case, we don't know F, so we just have to plug in a variable for it. And we would just say that we're using the magnitude of F1. And then we'd multiply that by the sine of 90. So we would just get positive 3 times the magnitude of F1. So this is another important step for statics problems. Oftentimes, we have to write an expression rather than a number for the torque. So it's important to write down an expression sometimes rather than a number. And one of the most important things you did there was that you put in the sign. It was good that you saw this would be positive, because this would be a counterclockwise torque. That's right. Now, let's actually work on this a little bit more. So what could you say then about the x? Something else we have to do for all the forces on these problems is break them into components. So what could you say about the x component of force 1? What is the x component of force 1?
So that would be 0.
That's right, because it's vertical, so it has no x component. And what could we write down for the y component of force 1?
So that would be, well, we don't know what that is. That would just be F.
Like this?
Yeah. Yeah.
Okay, now there's one important problem with this, which is remember we always need to put a sign in front of every expression.
Okay.
So
it'd be positive F1.
now remember, now we're working on the y component.
Oh, now we're back to forces. Okay, so that force would be negative.
Okay, so that is very important. Okay, so then this would end up being negative. That's right. And again, that's something that really messes people up on torque problems. Most people get messed up on on statics problems just with the setup. So this is an important part of the setup. For every single force, we have to decide its x component, its y component, and its torque. Sometimes I think students think that force is the same thing as torque, but you can see these are different things. And notice just because the sign on the torque is positive, that doesn't mean that the sign on the force is positive. They all have separate signs. So it's conventional to choose counterclockwise as the positive direction for torque, but up is the conventional positive direction for the y component. So it turns out to be really important to put in this negative sign. All right, so then this would be what we would generally write then for those. So good, that would be right. So let's also do so let's analyze force 2. First of all, what would be the x component for force 2?
So that's also 0.
Good. And what would be the y component for force 2?
So that's negative F2.
Negative. And here I'll put in a dot to show now this just stands for the magnitude, and we put in the sign. And what would be the torque for force 2?
So the torque of F2 would be F2 times D. And that is a negative torque because it's going clockwise.
Now that negative sign is really important. Good. So it's negative because this is a clockwise torque. I'd put a dot here then to show that this is just the magnitude, and this has an angle of 90. So the sine of 90 term drops out. So this is a key step again. Before we can start doing the algebra for statics, we have to take every single force and break it into an x component, a y component, and a torque. And oftentimes that will involve variables rather than numbers. And we have to be very careful to put in the right signs for all of those when we are doing that. That's good. Let's also do F3. So what would I write down for the x component of F3?
So that would be 0.
And how about the y component of F3?
That would be negative F3.
With a dot. And what would be the torque from force 3?
That's 0.
Because R would be 0 here. Now that might seem obvious, but students oftentimes get this wrong. I see a lot of students say, oh, the torque is 0, so this force doesn't matter. Oftentimes students think that since the torque is 0, the force doesn't matter. Well, the torque is 0, but that doesn't mean the force is 0. So my point is, even if the torque is 0, that doesn't mean that the x and y components are 0. Each of those has to be thought about separately. So that was correct. Okay, good. All right, so that's a basic review of a lot of the different types of torques you might have to find. And let's just start working on some problems here then, some statics problems. Okay. So let me give you this problem. Okay. Looks like this picture didn't come out to scale. But anyway, here's the picture that I wanted. And let's say, okay. Tell me when you have this written down.
Okay, so the plank has mass 6. Okay. What is the magnitude and direction of the force of the fulcrum on the plank? Okay.
Okay. So let's talk about this together a little bit. So let's see, is this what I wanted? One sec. One sec, let me make sure the problem will work. Okay, so let's change these numbers like I did that. Okay, and let's see. So why don't we go through this together so we can be going over a systematic method for these statics problems. Okay, so we can go through, do you have this other handout with you?
Yes.
Okay, so the important thing on these problems is to be systematic. These are not the kind of problems that you can just kind of wing it. We have to be systematic on these, so let's try that. So this is called a statics problem because the object is being held motionless. I didn't actually say that in the problem, so I guess I should have said, let's assume that the object is motionless. So if we assume that this object is motionless, step 1 is to choose your axes. And these are pretty much the conventional axes to choose, so we can always stick with that. You identify the main object that you're focusing on. So in this case, the main object would be this plank. I call that the main object because there's other objects in the problem like a person and a fulcrum. So what I have here is a plank that's resting on this fulcrum and there's a person that's pushing on it over here. Now the key for these problems is to make what we could call a force and torque table. Force.
Okay.
And torque table. So we begin that by identifying the object's weight. So what is the weight of this object?
So the weight of the plank.
That's right. So let's calculate that.
So
What
that
would its
would
weight be?
Calculator. So it'd be the 6 kilograms times 9.8.
Good.
So that's 58.8 newtons.
Good. So you remembered that weight is mg. So our weight would be 58.8 newtons. Now notice though here in step 3, we also have to identify the point of application of the plank's weight. So where is the plank's weight being applied?
So that's at the center of mass. So that would be at 15 meters.
That's right. So we need to draw that in at that position. And what's the direction of the weight?
Down.
So let's say that this is the weight here at a location of 15 meters. So what you're assuming on this problem is that the plank is uniform. If the plank has kind of a uniform density, then its center of mass will be in its center. So that's a good assumption. So we can assume the center of mass is in the center, and I told you the whole thing was 30 meters, so that would be at 15 meters. This doesn't seem like it came out to scale, but anyway, that's right. Okay, so that was actually one of the things I think you had mentioned in your email, having a little difficulty with the weight. So the first key is that the weight is applied at the object's center of mass. So here's that weight. What else do we have? We have to identify the forces from everything that is touching the object. So what's one of the things that's touching this object? What's another force here?
That would be the force from the person.
Yes, there's also the force of the person. And we know that's being applied here. I didn't tell you how big that is. So all I can do is call that F person. And what else is touching this object? Do you see any other objects that are touching the plank?
No, that's it. Well, just the fulcrum, but that won't cause any torque.
Okay, yeah. Now, it's true it won't cause a torque, but we can't ignore that. So that is something else we have to consider. There's also the force from the fulcrum, or the force from the pivot. So I can call that F, F for the force from the fulcrum. And what would be the direction? So where is that being applied? That's being applied here. And what's the direction of that force?
That's up.
And I don't know how big that is either. That's actually what the question was asking you for, right? We should have started by writing down a symbol for what the question's asking us, the force of the fulcrum. So that is certainly something that we have to take into account. So this is F for fulcrum, not F for friction. So we've identified the forces. So the only other forces come from things that are touching the object. All right, then step 5, we have to break each force into components. So for example, what would be the X component of the weight?
0.
And what would be the Y component of the weight?
58.8 newtons. And down, so negative.
That negative is really important. And we have to do the components including signs. That's crucial. Now, how about the force for the person? What is the X component of this force?
0.
And what would I write down for the Y component?
That's negative F person.
Right, with a dot, because now that's just the magnitude. And then we have the force from the fulcrum. So what's the X component of that force?
That's also 0.
And what's the Y component?
And that is positive F of fulcrum.
With a dot, because that's a magnitude. So that's our step 5, breaking each force into its components. So then we're ready for step 6. We have to choose the axis of rotation. That's pretty much always, now when you're doing a statics problem, you can choose any point you want to be the pivot point, because we're not actually rotating. So what do you think? What might be a good pivot point here?
The fulcrum.
Yeah, that seems, you could actually choose anything, but I think this is the one that would be the most intuitive. So let's choose the fulcrum as the pivot. Now, step 7, now we have to complete the force and torque table by determining the torque from every force, including signs. So what would be the torque from the weight?
So the torque from the weight would be 5.8 newtons times R, which would be 5 meters. And then that would be a clockwise torque. So that would be negative 294 newton meters.
Good. So it's good that you included the sign. How did you know this was clockwise? So you know that when you're trying to figure out the torque from each force, you pretend that as if that was the only force. So if this was the only force, it would cause a clockwise rotation. Therefore, it's a clockwise torque. So we can say that the torque from the weight is negative 294 Newton meters. Now we have to figure out the torque from the person's push.
Okay, so the torque from the person. Okay, so that would be, so it would be the force of the person times 20 times 5 meters. And that would be a positive torque because it's counterclockwise.
Good. So now we're using the person over here. So let's see, that's 5 meters because that's be 25 minus 20. So that would give us positive 5 FP. Okay, good. And then we have to do the torque from the fulcrum.
So that would be 0.
That's right. That would be 0 because R for that would be 0. Good. All right. Then you want to double check that everything has a sign. I think we got that right. Everything has a sign. So then we're ready to write down our Newton's second law equations, which is the framework for doing these problems. So the sum of the forces X equals MAX. Sum of the forces Y equals MAY. And the sum of the torques is the moment of inertia times the angular acceleration. What can we plug in for the for the x component of the acceleration?
If it's in, we're saying it's in equilibrium?
Yes.
Okay, so then it's 0.
Yeah, I forgot to write that down, but I should have said as part of this problem we're assuming that the plank is motionless. Assume the plank is motionless. Well, if it's motionless, it can't have any acceleration. So a sub x would be 0. And what do we plug in for a sub y?
A sub y is also 0.
Because it's motionless. And what do we plug in for the rotational acceleration alpha?
0.
Because it's not rotating either. So we can always do that. Step 10, you can always plug in 0 for a statics problem. And now we start plugging into the equations on the left-hand sides. You can work with these equations in any order, but oftentimes it's best to start with torque. So what torques should I plug in on the left-hand side of this equation?
So on the left-hand side, we should have 5 meters times the force from the person.
Anything else on the left-hand side?
Well, we can either, we can write minus the torque from the weight, or that can go, or we can set it equal to 0.
So the best thing is to always start with this equation and to plug in. So we should
Okay.
list all the torques on the left-hand side. What we're trying to develop here is a systematic method that will keep working for us as we
Okay.
get to problems that are harder and harder. So this is a good method to start with. This will work as the problems keep getting harder and harder. So there's only 2 torques to plug in here because this torque was 0. We should list them both on the left-hand side. It's best to work vertically here. So for example, notice I'm not doing this. I don't take the original equation and then just start adding on horizontally. That leads to people making mistakes. So instead, it's best to just work vertically, just like I'm writing this down. All right, now what? What could you do next?
So then I add 294 to both sides of the equation and solve for FP.
Good. And what do you get?
So then you get the force from the person is 58.8 newtons.
Notice that that came out positive. It had to, because remember, this symbol just stands for the magnitude now. If this had come out negative, that would actually tell us that we must have made a mistake, because this is just supposed to be a magnitude. But we know we're not done, because the problem wasn't asking us for the force from the person. It was asking us for the force from the fulcrum. So what could we do next? Well, now we simply plug into one of the other Newton's second laws. So now
I'm sorry, what was that?
we're not done yet because this is not what the question was asking us for. So what do we do now? We simply plug into the left-hand side of one of the other Newton's second laws. So let's plug into the y equation here. What could we list on the left-hand side of Newton's second law for the y equation?
So now we have the force from the person, which is 58.8 newtons. And we have the force from the weight, which is negative 58.8 newtons. And then we have the force from the fulcrum, which is unknown.
Whoa. Okay. I didn't mean to set up the problem like this, but okay. And then we have the force from the fulcrum. And on the right-hand side, we have a 0.
Mm-hmm.
Okay, good. Let's see. So we were plugging in the force of the weight, which is negative 58, and then the force of the person. Oh, okay. Is this what you have written down?
Yes.
Okay. So according to this seems to imply that the force of the fulcrum is 0, right?
Right.
All right. You've actually made a mistake here, though. Remember that we need to put a sign in front of every number. This, remember, was the force from the person. So should this be positive or negative?
The force from the person should be negative.
That makes a huge difference in our answer right there. Really, I guess what we should have done was gone back here and updated our table. Before we said the force from the person was negative Fp, but now we can be more specific and we can say it's negative 58.8. So whenever we can, we should go back and update this table here. So this should be a negative. So what's the force from the fulcrum?
So then the force from the fulcrum is 117.6 newtons.
Okay. So, what's the answer to the question?
117.6 newtons.
And remember, they were also asking you for the direction.
Oh, so in the positive direction?
That's right, or we could just say up now.
Okay.
Okay, so that's our first example of a complete statics problem. This is just about the easiest statics problem you'll ever see, but it was still a lot of steps. So there's a lot of steps that go into a statics problem, but the point is if we keep using the same systematic approach, we should be able to move on to harder and harder problems. Okay, so hopefully now you can see what the point of this force and torque table is. Before you start using Newton's second law, it's important to have a complete force and torque table so that we can know what are the x components to plug into the left-hand side here, what are the y components to plug in here, and what are the torques to plug in here. Usually, instructors don't usually make a table like this, but that's because they've done so many of these that they can kind of hold all this in their head. But for a beginner, it's really important to write everything on paper. So we need to write all of this stuff out up front before we start plugging in to Newton's second law. And then one of the real keys here is always putting in a sign, either a positive or a negative. Notice that all of our work was going to be wasted if we didn't put this negative sign in here. Right. All of the work we put in would have been for naught without that negative sign. One thing I didn't put in the handout that maybe I should have for the next edition is whenever possible, try to update your force and torque table. As soon as we figured out that this was Fp, we should have gone back and said that this was now the y component. Now we had more information about it. That may have helped us to avoid that mistake. But my general advice is don't write down any numbers without a sign. If you always write down a positive sign in front of the positive numbers, that will help you to notice when you need a negative sign in front of the negative numbers. Because if you get one sign wrong, all of our work won't come out correctly. Okay, so that was our method. So here is the correct force. So the key thing for these problems is we don't want to wing it. We have to do them all the same way. By the way, what would have happened if we tried to use the x equation here? Well, notice there are no x forces. There's no x forces, so if we tried to use the x equation, we would just get this, which would be very boring and uninteresting. So there are some problems where one of the equations turns out not to help. In this case, only the y and the torque equations helped, but other problems might be a little bit different. Okay, so it would be a good idea to go back and do this problem again. Like I said, this is just about the easiest problem that you could see, but you got to start somewhere. So you want to make sure that you're comfortable with this. And let me now give you some harder problems. So let's look at this. One second. Okay, hopefully this problem will work. Tell me when you have that written down.
Yes.
Okay, so so here's the problem. Maybe I should have written it. So I guess the 3 kilogram object is starting somewhere like this. Does this problem make any sense? So now the object is being moved towards the left, and eventually, so the plank is being held motionless, but eventually the plank will begin to tip. Actually, I don't think I need to tell you the plank is being held motionless. That really is implied by the problem. But eventually the plank is going to begin to tip when this moves far enough to the left. And we're trying to figure out what that location is. So this is a harder question than the one we did before. So let's try to be systematic and go through this step by step. So we can start with our axes. So what would be the main object, step 2, in this problem?
So step 2, to identify the object we're focusing on. So that's the weight.
Which weight?
The weight of the 3 kilogram weight.
Okay. Now, actually, that's not exactly what I mean by main object here. I would say the main object here is the plank. Because remember, this is a statics problem, and the question is, what does it take for the plank to remain motionless? I can see why you would think of this as the main object, because the question is focusing on that. But
Okay.
actually here, what we're treating as the main object is the extended object, the object that's extending over space that has to be held motionless. So in this case, we would say the plank is the main object. All right, then we begin the force and torque table by identifying the object's weight and its point of application. So what would be this object's weight?
So the weight is 49 newtons.
So let's see, the question was, if we keep moving the 3 kilogram object to the left, when will this start to tip? So what did you decide was the weight?
So the weight of the object
Yes.
is
I'm sorry. So yeah, which one do we mean here? So what we want is the weight of the main object, the plank.
okay. So that's 49 newtons,
Let's see. So I told
and
you
that's
the
going
old one.
down.
So the old problem I told you the mass of the plank was 5 kilograms. So 5 times 9.8 is 49 newtons. And what location is that in?
That's going down.
That's right.
So negative.
But what is the point of application of that? Where is that being applied?
Oh, that's it would be in the center of the plank, so
That's
at 10 meters.
So the weight of the plank is being applied here, and you've already figured out that must be half of 20, which is 10. All right, now we have to identify the forces from everything else that's touching the object. So what are the other forces on this object besides the weight of the plank?
So we have the weight from the object, or from the box.
Yeah, I'll call that the weight of the box. Good. So let's write that down. What would be that weight?
And that weight is 29.4 newtons.
3 times 9.8 is 29.4. And where's that being applied? Well, that's being applied to wherever the box is. All right.
Right.
What did we get for that? 29.4. Any other forces on the plank?
So we would have the forces from both of the pivot points going up, or both of the fulcrums going up.
We could call those two normal forces. So we could call that normal force 1 and normal force 2. And those are the only things that are touching the object. So that completes step 4. Step 5, break all the forces into components. So what would be the x component of the weight of the plank?
So that's 0.
Because it's vertical. And what's the y component of the weight of the plank?
That would be negative 49 newtons.
Good. And what's the x component of the weight of the box?
That's 0 as well.
And the x and the y component of the weight of the box?
Negative 29.4 newtons.
Good. It's good here that you're distinguishing between the kilograms, which is the mass, and the newtons, which is the weight. Then what's the x component of normal force 1?
0.
And the y component of normal force 1?
So we don't know what the y component is? Is that right?
That's true, but we've got to write something down so that we can do math. So what should we write down for the y component of normal force 1? That might have seemed like a weird question. What I mean by that is it going to be positive or negative?
So it's going to be positive.
And then since we don't know the magnitude, we'll just use the symbol for the magnitude. So at least we know the sign. So this might not seem like much, but it's important to write something down for each component, even if we don't know anything else about it. So what would I write down for the x component of normal force 2?
So that's 0.
And the y component of normal force 2?
So we can call it positive N2.
With a dot. All right. So that's our force and torque table. It's important to be real careful with that. We've broken everything into components. Choose the axis of rotation or pivot point. So what are you going to choose as your pivot point?
So in this problem, I'd probably choose point one.
What do you mean by point one?
I'm sorry.
What do you mean by that? Who's point one?
The first fulcrum, the
Good.
one that we called N1.
That is a good choice. So let's call this the pivot. It's always good to actually label the pivot. It's important to label that pivot. Now, step 7, now we have to determine the torque from each force. So what's the torque from the weight of the plank?
Okay, so this is I'm not really sure about.
Mm-hmm.
So I know it would be the force from the plank, which is 49 newtons, but if it's being, I guess it's since I'm like confused. It's being held in equilibrium, so I'm not sure like what to say for the direction of the torque and for R.
Okay, let's go through that together. So let's review how to find the torque here. So remember that our formula for torque was this. So remember that first thing we have to do is draw the R vector. So the R vector for this torque would go from where to where?
So it would go from the point of application, so that would be at 10 meters, to the pivot point.
Right. Really, it should go in the opposite direction, but that doesn't matter very much. So we'll draw it
Okay.
like this. So this is R for the weight of the plank. All right. Now, I think you were having some trouble figuring out what the sign for this should be. Now, here's the key. I briefly mentioned this before. When you're figuring, so what you want to do here is ask yourself, if this was the only force, would it cause clockwise or counterclockwise rotation?
It would cause a clockwise rotation.
Is that the positive or the negative direction?
That's negative.
So is the torque positive or negative?
It would be a negative torque.
So I think that's the answer to the question that you were asking a second ago. So it sounded like the thing you were having trouble with is you were saying, gee, if this is motionless, it's not going to rotate either clockwise or counterclockwise. Well, that's true, but when you're thinking about the torque from any individual force, you imagine that that's the only force. So what you need to say to yourself is, if this was the only force on the object, what type of rotation would it hypothetically cause? Well, if this was the only force, then hypothetically it would cause a clockwise torque. So therefore, this should be negative. Okay.
Okay.
Okay. So then what would we plug in for R?
So R would be 2 meters.
Let's see, because this is at 10 from the right, and that's at in the pivot. Oh, I'm confusing myself with my complicated picture. Let's see. So, yeah, so if this distance is 8 meters and this is in the center, that would be 2 meters. That's right. And what do I plug in for the force?
The force is the weight from the beam or from the plank.
Good. So what do I plug in for that?
Negative 49 newtons.
Just 49, right. We talked about that earlier. That's what this dot is supposed to remind us of. We're only plugging in the magnitude, because after all, remember, we already figured out the sign. If we plugged in another negative sign, we just cancel out all of our good work with the first negative sign. So
Okay.
that is a common mistake. So this is not a symbol that most instructors use, but I find it's really helpful to put these dots here to remind us that now we're only plugging in the magnitude for these. We already figured out the sign on our own. The y component has a negative sign, but now we're doing the torques. That's a common source of mistakes. And what would theta be here?
So that's negative 98 newton
Because
meters.
theta is 90. Good.
Oh, and sine is 90 degrees, so that would be just 1.
So what do I write down for the torque from the plank? Negative.
Negative 98 newton meters.
Okay, so this is some of the most important work for these statics problems, just correctly writing down the torques. So this would be a good example to have in your notes. Hopefully we're not making any mistakes. I think we got that right. All right, so now we have to go on to here. We need to figure out the torque from the weight of the box.
Okay. So we don't know where it is,
True.
right?
That's right.
So we could write, so we know that it's going to be a counterclockwise force. So we could say it's going to be 29.4 newtons times like X meters is what I would probably write.
Okay. And did you say the sign would be positive or negative?
It's going to be positive.
Good. So we should really have built that into our picture. So what does X stand for here?
X is the distance between, well, X would be the distance between the pivot point and the center of mass of the box.
That's right. Except because the box is not the main object, we're just treating it like a point object. We have to treat it like a point object because I didn't give you the dimensions. So we can just say X is the distance between the box and the pivot point. So maybe I'll write that over here. So here is our 3 kilogram object, and we just made up this distance here is X. We should have put this into the picture. So here's the weight of the box going down. And how did you know this is going to be positive? Well, you said if this was the only force on the object, it would cause a counterclockwise rotation. Therefore, it's in the positive direction. By the way, what's this question asking us for? What would be a good symbol for what this question is asking us?
X.
Yeah. We couldn't do that before because we had
or D for distance.
That's right. But if you're going to say D for distance, then you have to put a D down here as well because we want to be consistent. So D would not be a bad thing to say. But you decided to say maybe we should use D because we're using X to stand for X components. Let's call this D instead.
Okay.
D for distance. So I'll call this D for distance. Let's see. I erased the question here, but the question is, what distance does this have to be in when the plank just starts tipping, right? All right. So then that torque is going to be the torque of the weight of the box is positive 29.4 D. Okay. And then what would be the torque from normal force 1?
So that would be 0.
Because this force is being exerted right at the pivot. So R would be 0. Good.
Right.
And what would be the torque from normal force 2?
So that would be, so the distance is 8 meters. So it would be 8 times N2.
Okay, so what should I write down here for the torque from force 2?
I can't decide if it's, I guess it's a counterclockwise force. Is that right?
So what is it that's giving you difficulty about that? Why did you decide it was counterclockwise? Well, anyway, sorry. Yeah, so that's right. So remember, the key is ask yourself, if this was the only force on the object, which way would it make it rotate? And it would make it rotate counterclockwise. Remember that we have to be consistent. We're still thinking of this point as the pivot. We're still thinking of this as the pivot. Well, if we pushed up over here, that really would make us rotate counterclockwise. So you were correct. That should be positive. So it's good that you were thinking about that sign.
Okay.
Okay, so that's one of the hardest parts right there. You really want to take your time and make sure you get the force and torque table correctly. Hopefully we didn't make any mistakes there. So double check that each entry has a sign. I think we got that right. Now we write down our Newton's second law equations. Sum of the force X equals MAX. Sum of the force Y equals MAY. And sum of the torques equals 0. Equals I alpha. But what can we plug in on the right-hand side of these equations? What can we plug into the right-hand side of each of these equations?
0.
So we can write this. Now, what would we plug into the left-hand side of this equation? What happens if we plug into this equation?
I think I'm confused about what's the question?
Suppose we tried to plug into the x equation.
Oh, we would just have 0 equals 0.
That's right, because from our force and torque table, we can see there are no x components. So this equation basically drops out. So now we're basically, this is kind of like an algebra problem. However, do you see how many unknowns are there in this problem? How many variables are there that we don't know the value of? What are the unknowns?
1,
Let's
2,
try listing them.
3.
Yeah, what are the unknowns?
Well, there's the both the normal forces and the distance d, and we don't know the torque from one of the normal forces, so 4.
Now, that torque is not really a separate unknown, though, because notice it's just based on N2.
Okay, so then 3.
Good. And how many equations do we have left?
2.
Is that good or bad?
That's bad.
Yeah. We can't solve this because we have more unknowns than equations. So we must be missing something. There must be something else that we know that can allow us to plug in a number for one of these. This is where this problem gets tricky. Why don't you give this a little thought for a few seconds? What else do we know that would allow us to plug in a number for one of these variables?
So we can find the torque from N2.
How so?
Because we know that the sum of the torque should be 0, and we have 3 out of the 4 that are known.
So basically you're saying that you would use this equation here. So let's see, the problem with that, you can't actually figure that out because we don't know D. There's no point plugging into these equations yet because, again, we still have 2 equations and 3 unknowns. So there's something else that we know more directly about one of these. Remember, the question is asking us, what is the distance of this object when the plank just begins tipping? If you think about that, that tells us one of the other
Okay,
unknowns.
so then we know that once it begins tipping, it's going to lose contact with the pivot 2.
Good. So what variable does that tell us?
So then N2 would be 0.
That's right. That tells us that N2 is 0. So this problem is definitely harder than the one I gave you before. This is the key that most students won't see for this problem. Technically, there could be a normal force here, but if the plank is beginning to tip, remember that we know it's going to tip around this fulcrum over here. So if it starts to tip, it would be just on the verge of losing contact with this pivot. And if it's on the verge of losing contact, there would be no normal force. This should be 0. By the way, how did you know that we were going to pivot around here and not around here? Well, it's basically just common sense. We know that the rotation is going to be caused by moving this object here. So our common sense tells us that if we eventually have too much torque from this object, it's going to cause us to pivot around this fulcrum. So we'd be moving like this. Now, if we had noticed that earlier, we could have saved ourselves some work, because now we know what's the y component of normal force 2.
So then that would be 0.
And what's the torque from normal force 2?
0.
If we had figured that out earlier, we could have plugged that in from the start. In fact, if we had figured that out earlier, we could have just left out normal force 2 from the whole problem. If you'd wanted to, you could have just left out normal force 2 as soon as you realize that it doesn't come into play when the plank begins tipping. Okay, now we have 2 equations and 2 unknowns, so now it makes sense to start plugging into these equations down here. So how would that work? What would you plug in here?
So we'll use the sum of the torques
Right.
equals 0.
Good. So what would you plug into that?
So I would have 29.4 D minus 98 Newton meters equals 0.
Good. We should plug this in with the positive sign to make sure we're thinking about the signs. Good.
Okay.
And then what?
So then I would solve for D.
Good.
So then D equals 3.33 meters.
Okay, then what? Still there?
Yes.
Okay, good. So are we done?
Yes.
Okay. So that's our second statics problem. That one was harder than the earlier one because there was this hidden information about this normal force. So now we've finished step 10, and step 11 we plugged into the equations. Okay, notice the key thing is we tried to do this problem very similarly to the last problem. Identify all the forces, and then the key is to make this table. The key is to make this table of components and torques. And then we also saw this situation, if the object is just beginning to rotate, that gave us hidden information about this normal force. So that was important too. Notice that in this case, it turned out we never needed the y equation. It turned out that we never needed the y equation to answer this. If the question had also asked you to find n1, now we could find that from this equation. But since they didn't ask us that, we didn't need to use that equation. Okay, so this would be another good example to go back and try again. Okay, so here's a problem from your sample test. Let's see whether we've made some progress on this here. I guess we can try this. So remember that we want to try to do here is try to, again, be systematic and do each problem the same way. So try to keep going through the same steps that we were talking about. Oops, let me get that back before. Okay, so why don't you talk me through the steps here? Try to be systematic and go through the same steps that we went through before.
Okay, so first, first draw my picture. Okay, so the first step is to choose my axes, and I'm just going to make those the conventional axes. And then the main object. So my main object is my cat in this one.
I guess I didn't really define that very well in the handout. What I mean by the main object is the extended object that has a bunch of different forces being applied to it.
Okay, so my main object is my plank.
That's right.
Okay. Okay, so the main object's weight is given is 98 newtons.
10 times 9.8. Good.
Okay, and that's 98 newtons down, and that would be right from at 3 meters, right from the center of the plank. And then I'll find the weight of, well, the weight of the cat is unknown, but we know that that's applied 2 meters from F2. And then I want to make F2 my pivot. And I know there are no X forces on anything.
Good.
And I know that the Y component of the force of F2 is F2, and the Y component of F1 would be F1. And so now I would try to find the torques of everything. Okay, so Okay, so then if F2 is my pivot, then the torque from the plank is going to be, so I think is 6 meters. 6. So then I know that the weight is being applied 1 meter away from the pivot. So the torque from the weight of the plank would be 1 meter times 98 newtons, and that would be a counterclockwise torque. So that's positive 98 newton meters. And I would know that my torque from my cat would be a negative torque. And I don't know the weight from the cat yet, but we know that it's applied 2 meters away from the pivot point. And then the torque from F2 is 0 because that's my pivot. And the torque from F1 would be, let's see, would be F1 times, what's this distance? So that would be, let's see, 5. So that would be 3.4 meters. So the torque from F1 would be negative because it's counterclockwise, and it would be the force of F1 times 3.4 meters.
Because you knew that this was 0.6 meters from the left,
Right,
and this is 2
right.
meters from the right, and the whole thing is 6 meters. So that's good. I think you were careful with the distances there. That's good.
And then now I would use the sum of the torques equation. I mean, so it just begins. Oh, so it's like the last one. So it just begins to tip. So then actually then don't we have the same thing where F1, the torque from F1 would also be 0?
Okay, that's good.
Okay, so now so now we only have 2 torques. So now we know that so now we could write the sum of the torques equals 98 newton meters from the weight of the plank minus 2 meters times the weight of the cat equals 0.
Can you say that one more time?
If we write the sum of the torques equation, we have 98 newton meters from the weight of the plank minus 2 meters times the weight of the cat equals 0.
Good. So it's good that you saw this torque would be negative. Good.
And so now we can find the weight of the cat.
Okay.
So the weight of the cat would be so 49 newtons. Oh, but it wants the mass. Okay, so the weight of the cat would be 49 newtons, so then we know that the mass equals 5 kilograms. Okay.
So what's the answer to the question?
So it wants the mass of the cat. So the mass of the cat is 5 kilograms.
Okay. All right, so let's see here. You drew your picture. Now, on this problem, the geometry was kind of complicated. So the first thing you want to do is take all the distances and build them into the picture. This is 6 meters. This distance is 0.6 meters. This distance is 2 meters, so that you can find the distances that you need. So it sounded like you did that. And then in our force and torque table, we ended up with the weight of, so we needed this here, torque from the plank. It turned out that we didn't really need the y components, although we might have. All you ended up needing was the torque from the plank, but we could have said the y component here is negative 98. Force 2, that torque was 0. How did you know that the pivot is over here? That's just common sense, because they said it was going to begin to tip. Well, our common sense tells us that if the cat is making a tip, the cat would make a tip around the right-hand fulcrum. So that was a good choice. In this case, we really had to choose number 2 as the pivot. And then the key here that a lot of students wouldn't get is that since we're just beginning to tip, we're losing contact with fulcrum 1. So this would be 0. It turned out that I think you ended up doing a little unnecessary work, because at first you were trying to figure out the torques here, and then you realized that this is going to be 0. So nothing wrong with that, but the sooner we realize this will be 0, the less work we're going to end up doing. And then the weight of the cat was unknown, but we know that the torque from the cat would be negative 2 times that force. So then you just plug that into this equation. Okay, that's good. So that was a problem from the sample test, and it looks like we got that right. So that's good. So let's move on to even harder stuff. All right, so let's see. All right, so let's try to look now at some cases where maybe this will be harder. Okay. All right, so I think we made good progress with those horizontal objects. So now we have to try some of the harder problems that have non-horizontal objects. So now I have a plank. We could say that this over here is the wall, and this over here is the floor. And this here is what would be a plank or a ladder, say. So that's the plank, or oftentimes called a ladder. So now let's say this force here is 5 newtons. So try to figure out the torque from force 1.
So that force is not pushing down on the ladder, it's coming up?
Yeah, it's pushing up.
Okay. So it's pushing up, so that would cause a counterclockwise rotation. So that would be... Okay, so in this one, then I need to say, to find R, I would use 3 times cosine of 40. And then multiply that by the force, which would be... So then the torque from F1 would be 11.5 Newton meters.
Why did you take the cosine? It sounded like you were taking the cosine of 40. Why did you do that?
I'm sorry?
You said you were taking the cosine of 40?
Yes.
Why?
Right, because I want the distance, the perpendicular distance between F1 and the oh. Yeah, and the pivot.
Okay.
Which I guess I said the pivot would be the bottom of the ladder.
Okay, good. Yeah, so it sounds like you've decided to choose this as your pivot point. I think that's a good choice for these problems. For these types of ladder problems, your instructor in the answer key always chooses this point as the pivot, so we may as well follow that. All right, now I think you worked that out correctly. I just want to point out here that you're actually using a different method for finding torque than the one that we went over before. Now, if you go back to the handout on torque, now you're using what's called the R perpendicular method for finding torque. Why are you doing that? Why, excuse me, why can't we just say this is RF sine 40? Why can't we just plug in 40 for theta here?
Because 40 is not the angle between the force and the pivot.
Between the force and R.
Force and R.
Yeah, that's right. This is what I meant earlier when I said that just because they give you an angle doesn't mean they're giving you theta. We need to know theta, the angle between the force and the R vector. But this is not the angle between the force and the R vector. So now there's two things we could do. We could use geometry to figure out the angle between the force and the R vector. That's not that hard. That would be a perfectly good approach. But I noticed from the answer keys to your test, that's not the way your instructor does it. Instead, on these problems, your instructor switches over to the R perpendicular method. And that's what you were just doing a second ago, too. So that's fine. So let's just be systematic about that, although I think you did that correctly. So here's the pivot point. Here's the force. Now you have to draw the line of the force, step 3. So the line of the force would be this. The line of the force is just a line that goes through the force, through the point of application. Now, instead of drawing R, we're going to draw R perpendicular in this method. And R perpendicular goes from the axis of rotation perpendicular to the line of the force. So R perpendicular here.
In these kind of instances where I'm like drawing the line of the force, it doesn't matter how long I make it. Like that doesn't matter.
That's right. So the line of the force is just an infinite line that runs through the point of application of the force and parallel to F. So how long should you draw it? You should just draw it however long is necessary for it to intersect with R perpendicular. Okay. You just have to draw it so that it's long enough to intersect with R perpendicular. So for example, it would be a waste of time to keep drawing it down here because we didn't need that. And it would be a waste to keep drawing it up here because we didn't need that. So you just draw however long you need it so that it can intersect with R perpendicular. But we need some line because R perpendicular is not going to intersect with the force itself. It's just going to intersect with the line of the force. So now we draw R perpendicular from the axis of rotation perpendicular to the line of the force. So here would be our R perpendicular vector. And now we're going to use a different equation for torque. Now instead of using RF sine theta, now we're going to use R perpendicular times F. Now in this case, I think you figured out that this would be, did you say clockwise or counterclockwise?
I said it would be counterclockwise.
So would the torque be positive or negative?
Positive.
Now think about that again. To determine the sign, you should ask, would the force make the R perpendicular vector rotate clockwise or counterclockwise? So if this upward force was being exerted on this vector, would it make it rotate clockwise or counterclockwise?
Oh, because the pivot point, the pivot point is on the bottom, right. So that would be a clockwise torque. That would be a negative.
Okay, I didn't realize that at first. I think that was a mistake before. Yeah, so that's why we always have to label the pivot from the start. If you can't label the pivot, there's no way to figure out whether it's plus or minus. You could have chosen anything you want to be the pivot, but since we chose this, the torque is going to be negative. So that's very crucial. We saw how important signs were on the earlier problems. Now, what's R perpendicular's length going to be here? Well, now that's a geometry question. R perpendicular is part of this little right triangle with a hypotenuse of 3 meters. So we could say that cosine of 30 is the adjacent side over the hypotenuse. So R perpendicular is 3 cosine 30. So that's why you were correct in this case to use the cosine 3. So we would get
Cosine 40 degrees.
Thank you. So this would be 3 cosine 40. And then the force is 5. And as usual, we're just pulling in magnitudes here. So 3 cosine 40 times 5. And what did you get as your answer?
Negative 11.5 Newton meters.
Okay. So it sounds like this is a method you already knew about because you applied this on your own. So this is what's called the R perpendicular approach, because now we're not drawing R, we're drawing R perpendicular. Now, you could have used the old method. You could have used the old method if you just used geometry to figure out the angle between R and F. But your instructor does these problems using the R perpendicular approach, so it'll probably be easier to follow the answer key if you do them the same way. And it sounds like you were already kind of doing it that way. Okay, that's
So
good.
if I was trying to use the angle between R and the force, wouldn't that be 90?
That would be a little bit of a tricky geometry problem. So first of all, so you're saying that you want to try doing the R method as well?
Yeah, I'm just
Okay.
trying to
So did you draw
figure
the
out
R
like
vector?
which would be the angle to use.
Okay. Well, the first thing then is you've got to draw the R vector. So how would you draw the R vector?
So then the R vector is just that 3 meters between the pivot and the force.
That's right, but we have to draw that as a vector, so it would look like this. I'll draw it right on top. So it would just be this line here.
Mm-hmm.
So now label the angle between F and R. I think you said it was 90, but I think now you can see it's not 90.
Oh,
It would
so
be
then
this
that would
angle
be the
or this
oh,
angle.
so then that would be the angle right in that corner.
Yeah,
Okay.
so you could use either this acute angle or this obtuse one. Either one will give you the same outcome. And you could use geometry to figure out those angles. But like I said, that's not the way your instructor does it in the answer keys. It's actually less work just to use the R perpendicular method, because then you don't have to move any angles around. You can see it is a little bit tricky because you got to look at these angles up here. All right, so it's probably better just to work with one method. You did this correctly the first time, so we may as well just stick with that. Okay, so I did want to point out, usually you can use either method, but usually one of them is easier than the other. In this case, I think the R perpendicular method is easier. But that does show you the difference between R and R perpendicular. This would be the R vector from the pivot to the point of application of the force, and this is the R perpendicular vector from the pivot perpendicular to the line of the force. So those are actually two different vectors. Okay, but you did this correctly the first time, and this is how your instructor does it. So I guess it's best to stick with the R perpendicular method here. Okay, very good. So that would give us that torque. The one part that you got wrong before, I think, was the sign. But remember, that's important. If we get one sign wrong, all the other answers are going to come out incorrectly. So that's an important thing to watch out for. So let's draw this. If we can get the torques right, the rest of the statics problem is oftentimes not that difficult. The key thing is getting those torques. Let's say this is 50 degrees. Okay, so let's find torque 1.
Okay, so I would use the R perpendicular method. So if I choose the bottom as my pivot, I think I actually want to use the top as my pivot point. So then I would have a clockwise rotation. And the torque would equal 9 times 6 cosine of 50 degrees. So my torque would be negative 34.7 Newton meters.
Negative. Did you say you were choosing this point as the pivot?
I said the top, like the wall would be the pivot.
Like this point here?
Yes.
Now you're using the R perpendicular approach, so our formula will look like this. Did you draw the line of force?
Yeah, so I extended the force down
Good.
to the base of the triangle that's drawn, and then my moment arm would be from that line of the oh wait, so that's not right. Okay, so the way I did it, then I made the bottom the pivot.
Okay, yeah. You said you were using the top as the pivot, but if you were going to do that, then this would be R perpendicular, right?
Right.
And we actually can't do that because I didn't give you this distance. I didn't give you that dimension, so it would be impossible to figure out the torque around this pivot because you don't know what that distance is. I don't think there's enough information to work that out. All right.
Okay.
So I think.
So then in this case, so I made the bottom point my pivot.
Yeah.
So in that case, I'm rotating the ladder would be rotating. It would still be rotating clockwise. Is that right?
Yeah. Around this pivot, this force would make you rotate clockwise. That's right. So would it be positive or negative?
It would be negative.
Good. Okay. And then this then is R perpendicular from the pivot point perpendicular to the line of the force. And now this is adjacent to the 50-degree angle, which means that R perpendicular is going to be 6 cosine 50. And the force is, what should I plug in for the force?
9 newtons.
Not negative 9, but just 9, because we're just plugging in the magnitude.
Okay.
And then we'll get negative 34.7. So I think there was a mistake in the way you were describing your method, but I guess you came out with the right answer. So maybe, yeah, there seemed to have been some confusion there. You ended up with the right answer. I think it's best to choose, for these problems, you may as well choose the bottom point as the pivot because that's how your instructor seems to do it in the answer key. So it'll make it easier to check your work if you usually do that. And in this case, you had to because we didn't know any of the other distances. So I think we ended up with the negative 34.7. Again, the R method would not be as easy because we don't know the angle between F and R. 50 is not the angle between F and R, so the R perpendicular method is better in that case.
Actually, if I chose the bottom as the pivot and I have weight pushing down from the top, wouldn't that give me a counterclockwise rotation?
Are we getting confused here? Maybe you caught our mistake. Yep, I guess we got confused. It's good that you thought about that again. All right, so now here's this force pushing down. This would make us rotate. Yeah, why did we think it was clockwise? I don't know. We got confused. So I guess our first answer was wrong then. It was right for the top pivot. All right, so now what's your new answer?
Okay. Yeah, I think I was getting confused earlier just because I was thinking that if it was touching the wall, then it wouldn't rotate, but it would still rotate down even if the bottom was then like sliding on the floor.
Yeah, so there would be a type of rotation there. That's right. Okay. Remember that we're supposed to imagine how would this rotate if this was the only force? Well, that means that you should be imagining that there is no wall.
Okay.
Because then you're imagining if there was no normal force from the wall, we really could rotate in this direction. So that's one of the keys here. When you're trying to figure out the direction of the torque, you really need to imagine that that's the only force on the object, which includes meaning you'd have to imagine that there was no normal force from the wall, which is like imagining that the wall wasn't there. We have to think about each force separately from all the other forces. So what did we come out now as our answer? What's the torque from force 1?
That would be 34.7 Newton meters.
Positive or negative? Should that be positive or negative?
Positive.
Yeah, that was our mistake before. So this should be positive. Okay, yeah, if you were choosing the top as the pivot, I guess it would come out negative. But now that we're choosing the bottom, so you really have to double check all your steps here because one little mistake can mess up all of our algebra. But now I think we got it right. Sometimes what I like to do is I just like to ask, which way would the force make r perpendicular rotate? If the force was being exerted on r perpendicular, it would make it rotate counterclockwise. So that would be positive. So we came out with a positive torque there. So let's figure out the torque from force 1 here.
It's 6 newtons. Okay. Okay, so if I have this force here and my pivot is at the bottom, then it's going to be a clockwise rotation. So the torque is going to be negative. And then it would be 10. So the moment arm would be 10 times cosine of 20 degrees, and then times the 6 newtons. So then the final answer for torque would be negative 56.4 Newton meters.
Like this?
Yes.
Okay. Now, let's make sure we were systematic. You drew the pivot point. Good. We've got F. Did you draw the line of force?
Yeah, so the line, oh, I guess I just said the line of force was down, but that's not right.
Yeah, where is the line of force?
Okay, I'm going to start over.
Okay,
Okay, so then the line of force would be horizontal. It's not,
Right.
It's not down, it's horizontal.
Horizontal through this point here.
Right.
Okay.
Okay, so I screwed that up. Okay.
Yeah, so let's try again.
So in this case, okay, let me erase this. Okay, so it's still a clockwise rotation, but now I have 10 meters. And I want so okay. Okay, so now I think the force is negative 20.5 Newton meters. So I continued F over, and then I drew a line from F to the pivot point.
So that's a vertical line, right?
Yes, I drew a vertical line from F to the pivot.
That's R perpendicular. So R perpendicular is, so that's our step 4. From the axis of rotation perpendicular to the line of the force. Good.
Right, and then I knew that the hypotenuse of that triangle is, oh wait, So then I knew that the hypotenuse of that triangle was 10 meters.
Right.
And then the calculations I did, I said that oh, I guess I didn't need to do that. I said that the angle next to 20 degrees was 70, but I'm not sure I needed to do that.
Okay.
Also, I found the length of R perpendicular, and I said that was 3.4 meters.
And how did you find that length? What calculation
So I
did you
did, the hypotenuse is 10 times cosine of 70.
Because this side of the triangle is adjacent to the 70. Okay, good.
And then I multiplied that by 6, which is the force.
And was it positive or negative? The torque?
The torque should be negative.
We got that right before. And what did you get as your answer?
Negative 20.5 Newton meters.
Okay, good. So our first answer was incorrect, so it's good that we went over this. How did I fake you out here? Well, I shifted from vertical to horizontal forces, and it turns out that the analysis is different. So it's important to analyze each force separately. The picture that you see on the test is always going to be a little bit different than the examples that you've seen before. So you just have to adapt to each new problem. One thing that probably went wrong here is I suspect that you probably didn't draw the line of the force or R perpendicular. You might have done those steps in your head, and that might have gotten us confused. So it's important to actually draw the line of the force and to actually draw R perpendicular. I think that you were kind of thinking that maybe this was R perpendicular, but that turns out to be incorrect. So the method, are you still there?
Yes.
Good. The method you used there was good. You didn't quite do it exactly the way, so the method you used was fine. Let me show you how your instructor does this, because they do it a little bit differently. Okay. Although, like I said, your method here is fine if you prefer it. But what your instructor does is, a lot of time physicists prefer to use the angle that's given. So a physicist might not like to use this 70-degree angle because it wasn't given. There's no real reason for that, but they tend to not do that. So what a physicist would do is they would say, well, what we really need to know is how long this line is. But isn't that line the same length as this line? We could just as well say this is R perpendicular. And now we can use this angle to figure out R perpendicular, because now we can use the bottom triangle.
Okay, so then it would be so then it would be 10 sine 20 would be that length.
That's right, because now R perpendicular is opposite to the angle that we know here. It's opposite to this 20-degree angle. But I think if you do the calculation, you'll get the same exact answer either way, because now we would have that the torque is negative 10 sine 20 times 6, because the sine of 20 is the same as the cosine of 70.
Right. So then it doesn't really matter so in this case, even though the 6 Newton force was pointing to the right, I can extend that line to the left and then draw the moment arm, and it's the same.
Yeah, well, the safest thing is to first draw the moment arm here, from the pivot point to the line of application of the force. But remember, all we really care about is the magnitude of R perpendicular. That is, we just care about the length of this vector. Well, that's the same length as this over here. So the point is, rather than figuring out the length over here, it might be more convenient to figure out the length over here. At least that's the way your instructor prefers to do it. Like I'm saying, I'm sure you would get full credit if you did it your way. I'm just pointing this out so you can understand what they're doing in the answer key. So you can really really do it whichever way feels more comfortable for you. Either of these is fine, but instructors usually prefer to use this method because then they can use the original angle that they were given. There's not any real advantage to that, but that's just what they do. Okay, so but either way, we're going to get the same answer. The one thing that we can't do, so notice it doesn't matter whether we use cosine of 70 or sine of 20 because those are the same. The one thing we can't do is take the cosine of 20, which was our first instinct, because that gives us the wrong answer. So it really is important to draw the R perpendicular vector each time. If we try to do that in our head, it's easy to get confused. And this is really the hardest part of these statics problems, just getting the torques right. If we can just learn how to get all these torques right, the rest of it is really just algebra. Okay, so So I think we worked that out. So the big lesson here is don't skip steps 3 and 4. Really do draw the line of force and really do draw R perpendicular. That might mean that you want to have a maybe if there's many forces, you might want to keep drawing separate little pictures for each torque, because otherwise the pictures can tend to get overloaded. Okay, so let's look at this. All right, so here's force 1, 3 newtons to the left. Try to figure out the torque from force 1.
Okay. This is 15. Okay, so in this case, my R perpendicular would be, I'll do his method. So that would be sine of 8 times sine of 15 degrees. And then times 3 newtons for the overall torque. And I know that this would be a counterclockwise torque. So it would be positive. That would be 3 times 8 times sine 15. Which yields 6.2 newton meters.
Positive 6.2.
I actually think his way is a little easier.
Sure, that's fine. All right, so
to not have to find the other angle and just use the angle that you're given.
Okay, good. Now, first of all, so you're using the R perpendicular method again here. Why are you not using the R method? Because to use the R method, we'd have to know theta. And theta is the angle between R and F, and we don't know that angle. We could figure it out, but it wasn't given to us. This is not theta. This is not the angle between R and F. So your instructor prefers to use the R perpendicular method here. That probably is easier. So technically, R perpendicular should first be drawn over here, from the pivot point to the line of application of the force. But all we care about is its magnitude. So then we can move it over here. And now this is opposite to the 15, so you should use the sine. So it looks like that came out right. 8 times sine 15 times 3. Okay, so that one seemed like it came out correctly. So notice you can't just memorize always use sine or always use cosine, because some of these problems we're using the sine and some we're using the cosine. If you're doing the R method, you always use the sine, but then you need to know the angle between R and F. If you're using the R perpendicular method, it's a matter of geometry, and you have to decide whether you're using the sine or the cosine. On the previous problem, at first you were using the cosine, probably because we did that on the previous problems, but here we're back to the sine. Okay, so I think we got that. Correct. Let's call this F1 5 newtons. This is 7 meters. This is 25 degrees. So let's find torque 1.
Okay, so in this case, I would use the same R perpendicular method, and so then R perpendicular would be 7 times the cosine of 25 degrees. And then I'm going to multiply it by the force that I was given, which is 5 newtons. And in this case, it would, if my pivot is at the bottom, it would be a clockwise torque. So it would be a negative overall torque. And so the final answer would be the torque from force 1 would be negative 31.7 Newton meters.
Clockwise. All right, so now we're going back to a vertical force. Here the line of the force would look like this. So R perpendicular would be this from the pivot point to the line of the force, and it's adjacent to the 25. So we're back to using the cosine. That seems like that's right. So yes, so torque 1 here would be negative 31.7 Newton meters. And what would be, remember that in our force and torque table, we also have to do this. So what would we write down for the x component of this force? What would be the x component of force 1?
So that would be the 7 cosine of 25 degrees. So that's, let me do the math. That is 6.3 approximately.
6.3, what would be the units on that?
6.3 meters. Or, no, I'm sorry, 6.3 newtons.
I think you got a little confused there. So remember that we're trying to find the x component of force 1. How big is force 1?
Oh, I'm sorry. The x component of force 1 is 0.
That's right. I think you actually ended up finding R perpendicular again there. You were kind of finding the x component of the distance. There's so many numbers flying around, it's easy to get confused. So, so that should be 0 because we want the x component of the force. And what would be F1 sub y, the y component of the force?
That's 5 newtons.
Good, except we want to be in the habit of always putting a sign out in front.
So positive 5 newtons.
Good. Notice that just because the torque is negative doesn't mean the force is negative. The torque here is negative, but the force is positive. So those would be part of making our force and torque table for this problem. And let's say we've got here force 2, 7 newtons. So what would be force 2x?
Okay, so force 2 of x, is that right on the pivot?
Yes.
Right on the bottom? So force 2 of x would be 0 again.
And force 2y?
That would be negative 7 newtons.
And torque from force 2?
That would be 0.
Because we've already decided that this point down here is our pivot, and we know that now both R and R perpendicular would be 0. When we're right on the pivot, that's 0. But notice that doesn't mean that there's no force. There's still a force that we have to take into account. And let's also, at this point, do F3, 6 newtons. So what would be F3x?
Okay, so f of x3 is 6 newtons. So then Fy of F3 of y is 0. And then the torque from F3 is also 0.
Okay, that's good. The only problem is we want to get in the habit of always putting a sign in front of every number. So what should be the sign here?
Okay, so from the x component of force 3 is positive 6 newtons.
And the reason you want to do that is that way it just reminds you to think about the sign. So if it turned out to be negative, at least we've thought about it, and we have a good chance to catch that. Okay, so now we've started to see, we started with just horizontal objects, and there was a problem like that in the sample test. But you're also likely to see problems with diagonal objects, and then it can be more difficult to find the torque. We saw that sometimes it helps to use this R perpendicular method instead. And the key there is to actually draw the line of the force and to draw the r perpendicular vector. And the key thing is, if you're going to use the r method, you need to remember that only works if you know the angle between r and f. Just because they gave you an angle doesn't mean that's the angle between r and f. So in these cases, it was actually easier to use r perpendicular. Okay, well, that's our time. So unfortunately, we won't get to do a full statics problem with an object like this. But we went through the most important first step, which is how to find the torques for that. That's oftentimes something that gives people the most trouble. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you.